Welcome everyone. Good morning. My name is Marco. I will be moderating today's webinar on behalf of ETA Florence. We just wait for participants to join. So first introduction about this webinar. This event has been co-organized by the Horizon Europe projects, HYPER and ELOXYCHEM, bringing together experts from both initiatives as well as leading companies to present innovative electrochemical pathways and solutions. So before we begin, just a couple of quick reminders. Today's session is being recorded and the presentations will be shared afterwards. And please use the chat for general comments. And you can find a Q&A box below for any questions you may have. So let's just wait another minute or two. Then we begin with the first presentation. So today we start with the industrial contribution from Andreas Stavmikalis. Andreas is a chemical engineer, part of Evonik since 2007. Evonik is a global chemical company headquartered in Essen, Germany, which is active in more than 100 countries, generating sales for 15.2 billion in 2024. In his position, Andreas is a consultant in the public funding departments of Evonik, and he supports the R&D and operative units at all aspects of public funding. So Andreas, when you want, the floor is yours. Please enable the mic.
Yeah, thank you very much, Marco, for the introduction. I will share my screen and then I can start right away with my presentation about sustainability, innovation, and electrochemistry at Evonik. Evonik has developed for itself a sustainability strategy, and the strategy includes certain targets concerning sustainability. The targets are addressing two different categories, I would say. One category we call next-gen solutions. That means products which we produce, which have a positive sustainability impact at the application. I will give examples later on. In this context, we also talk about the term handprint. The other category we call next-gen technologies. That means the impact of the production of our products on the environment. And in this context, we also talk about the term footprint. Concerning next-gen solutions at handprint, the most important target is that we want to achieve a share of our sales by 2030 of 50% of such next-gen solutions products, which means products with a positive impact at their application. And concerning the category next-gen technologies, the footprint, our targets are to reduce our greenhouse gas emissions for the production processes, by 2030 by 25% for scope 1 and 2, and by reduce the emissions of scope 3 by 11%. On this slide, I have some examples about our next-gen solutions. We give you a few examples in the category of circular economy. For example, we produce catalysts which are enabling recycling processes. We also produce additives which enable polyurethane recycling. Other examples, for example, in the energy transition category, we produce and have developed and produced membranes for separation of hydrogen from biogas. Also materials for wind power plants and photovoltaic plants. There are also some materials, absorption materials for carbon capture. And in the field of biosolutions, examples are that we produce bio-based and fully biodegradable surfactants and biodegradable and active cosmetic ingredients. Next slide is about the next-gen technologies. This is about reduction of our greenhouse gas emissions. We are taking several measures to reduce our greenhouse gas emissions. One example is that we stopped our own power generation in our biggest production site in the city of Marl in Germany, which was coal-based. We invested into high efficient gas power plants, combined cycle, and with combined heat and power generation. And they can also be operated by biogas, and as a future option, also use of green hydrogen would be possible. The next generation technologies itself, there we have defined three different options. The first one we call advanced levers, which is, for example, advanced process control. Second option is innovative waste heat upcycling, for example, which by using heat pumps to convert waste heat into usable process heat, which is needed for our production processes. Third option is a redesign of our production processes. And additionally, measure is to use renewable energy. We have concluded power purchase agreements with wind park operators and also solar park operators to provide us with renewable electricity. Now I come to the topic research, development, and innovation at Evonik, because to realize all the greenhouse gas saving potential, we also need research, development, and innovation. And therefore, we have RD&I activities in the fields of circular economy, in energy transition, in biotechnology, in using CO2 as feedstock in our production plants, process efficiency, and of course, the main topic of today in electrochemistry. On the right-hand side, you see some data about our RD&I activities of the year 2024. Now I come to the topic electrochemistry at Evonik. We estimate that the carbon footprint of around 1/5 of our Evonik process steps can be significantly reduced through the use of electrochemistry. Because of electrochemistry, we can achieve reduced energy consumption, reduced use of raw materials, less CO2 emissions, and lower environmental impact, for example, by salt loads from wastewater, industrial wastewater, of course. And therefore, Evonik is exploring ways to make greater use of electrochemical processes and products. It has bundled its group-wide expertise in electrochemical process in the technology platform, which we call Electrochemical Process and Products. This technology platform we have established in 2022, and there are actually around 20 employees working in this unit. And before I show you our individual electrochemistry projects, I would like to show you something about our motivation to conduct our RD&I activities also within public funding projects. A few years ago, we have made a survey over our project leaders who are leading public funding projects at Evonik. and asked them about their motivation to use public funding in their RD&I activities. And relatively surprisingly, it turned out that the cash-in was not the most important motivation. The most important motivation was the technology development and access to external knowledge, which means which we have possibility to access external knowledge is because in virtually all public funding projects we work together with other partners in a project consortium, and that was the most important motivation. Other motivation was to get market access to markets where we are not active now, but we want to be active in the future. And if we have the right partners in the project consortium, we can learn about these new markets which we want to enter with our new developments. And yeah, the other reasons include to enlarge the network, to be part of the value chain, and to increase our reputation. On the right-hand side, I have collected some figures about our public funding projects, the currently running public funding projects at Evonik. There are 7 projects running with EU funding, 26 with funding from German state, 3 projects funded by certain German regions, and 6 projects with funding of other countries, partly inside European Union, partly also outside European Union. In total, we have currently 42 public funding projects running at Evonik. Okay, now I come to the individual projects in the field of electrochemistry. The first line is the ELOXYCHEM Project. I think in the next presentations you will more learn about this project. Another project is called µ. It's about electrochemical carboxylation of multiple bond systems to free carboxylic acids. The power to value chemicals is about CO2 electrolysis to carbon monoxide in order to use this as feedstock for chemical production. Another topic is electrodialysis. They were working on to use the electrodialysis for salt separation for industrial wastewater treatment and reuse. Liberate, lignin biorefinery approach using electrochemical flow. Limnoplast, microplastics in Europe's freshwater ecosystems, and the part of Evonik in this project is to develop an electrostatic separation of nano and microplastics from wastewater. Early is about extraction and purification of lithium from used electromobility lithium-ion batteries for battery cell manufacturing. Then we have a project REM Direct. It's about direct coating of anion conducting membranes for large-scale water electrolyzers. And Reticus is about artificial photosynthesis by combination of electrolysis and biotechnology. And the last one here, DAC to methanol lab, is about a combination of direct air capture, water electrolysis, and methanol synthesis. Okay, the next 3 slides are just giving some more information about a few of these mentioned projects. This one about the Liberate project. The next one is about our electrodialysis and the Limnoplast project. And the last one gives some more information about our Reticus project. Yeah, that's the end of my presentation. Thank you for your attention. And if there are any questions, I will do my best to give answers.
Thank you, Andreas, for the insightful presentation on Evonik and on the projects you're following and leading at your company. So I wait for any questions. Otherwise, we can proceed. Okay. I don't see any specific questions in the Q&A box. So I would say we can proceed with the IPER project. So I will now give the floor to Richard Ain Chief Research Scientist at Sintef Industry in Oslo, Norway. He is the coordinator of the ÆLECTRA Project. In addition to leading EU projects, Richard is also Vice Chair for Circular Innovation of the Advisory and Programming Group in the European Process Industries Private-Public Partnership Processes for Planet. So when you want, the floor is yours. Please enable the mic. Thank you.
Okay, thank you very much, Marco, for the introduction. Good morning to all participants. As Marco indicated, I will be talking about what we call the HYPER project, and you see the full title here on the screen. And the point of the HYPER project is to develop a scalable modular electrochemical process for the production of hydrogen peroxide, which we aim to have a better footprint than the current state of the art. One of the really neat things I think about the project is that we, in addition to developing this electrochemical process, we're seeing how that technology can be integrated into 3 downstream sectors. The 3 sectors are textiles, where hydrogen peroxide is used for the bleaching of cotton and other textile fibers. And in this case, what we call our hydrogen peroxide will be used in bleaching technologies in the textile industry. Pulp and paper is the other sector where hydrogen peroxide is also used for bleaching. And the integration of that sector in the project is more a paper study to see how we could integrate our process into the pulp mill and reduce the use of other non-environmentally friendly oxidants. And finally, is chemicals and polymers, where hydrogen peroxide is used for epoxidation and emulsion polymerizations. And in that sector, we'll be doing 5 to 100-hour tests of our TR06 demo. So the state of the art. The state of the art is known as the anthraquinone or auto-oxidation process. And in this process, the anthraquinone, which is a aromatic organic molecule, is a hydrogen carrier. So it is essentially a way to achieve a hydrogen plus oxygen type of reaction. So despite the fact that hydrogen peroxide doesn't have any carbon, this is a fossil carbon-based process because the hydrogen is sourced from fossil fuels through the steaming forming of methane. And as you see on the right-hand side here, it's a rather complicated process. So you have the hydrogenation, you have the oxidation, you have a process to recover the palladium catalyst that is used for the hydrogenation. It goes through a number of steps to purify the hydrogen peroxide. And importantly, the process has this, what I like to call a cocktail of organic solvents. So you have to have lots of different organic solvents in order to keep everything in solution to get the process to go. And then finally, this is done in very large scale in centralized locations. So you then have to ship the hydrogen peroxide, which is in usually 50% concentration, to all of the sites in Europe where you want to hydrogen peroxide is used, in all the textile facilities and all the pulp and paper facilities. And so, since hydrogen peroxide is unstable, this requires the addition of stabilizers, which to ensure that when it arrives at the site, it's still 50% solution. By shipping all this means that half of the weight that you're shipping around Europe is water. And this is not particularly environmentally friendly as well, in addition to the fact that you're using a fossil carbon feedstock to make your hydrogen. So what we want to do in HYPER is to do this electrically. And what we're starting with is sulfuric acid. And we're then doing an oxidation of that sulfuric acid to make make persulfate. When we wrote the proposal, we had imagined that you could store this persulfate and use this as sort of a chemical energy, electricity storage medium. Unfortunately, that's not the way the project has worked out. But then after you make the persulfate, you then go through what we call the utilizer, which does the hydrolysis of the persulfate to hydrogen peroxide, and then takes the sulfate back to the electrolyzer. On the cathode side, we're looking primarily at the production of hydrogen, but we're also looking at other value-added products we can get from the cathode that may be beneficial to our downstream industries. So the goals of the project is to reduce CO2 emissions by 75%, reduce the energy consumption by 33%, and have a more economical process as compared to the AO process, which is our benchmark. We're using water as a solvent. We have no catalyst or stabilizers, so all of this should also help all of the downstream processes because they don't have to handle all of the extra chemicals needed for the hydrogen peroxide stabilization. Very briefly, some of the R&D accomplishments that I really can't talk about, but I wanted to share with you is that so far the project has developed cheaper electrode coatings with comparable activity and stability to what we had started with. We also have an improved electrochemical cell design with increased efficiencies. And as I indicated, we are looking at compatible cathodic reactions of relevance. So, for example, we have working on a process for the reduction of indigo to leuco-indigo to give a more sustainable dyeing process for the textile industry. We're also looking at how to use some byproducts from the pulp mill process as an electrolyte in the entire electrochemistry. But the most important thing that we've accomplished right now is this TRL 4 to 5 mini plant deployment. And this gives you an idea of what that mini plant looks like. Over here on the left-hand side, you have the electrolyzer, and that is a relatively straightforward process. Electricity comes in, you have water, you have the sulfate, you get hydrogen out, and then you have the persulfate, which goes into the utilizer. And the utilizer is actually a set of 4 different processes. So you have the persulfate that comes in first to the evaporator, and the point of the evaporator is to provide a persulfate solution which is optimal for hydrolysis. A lot of work has been done to determine what the best solution composition is for that hydrolysis, and so this is why we have this step. You have some hydrogen peroxide, but you have primarily optimal persulfate sulfate solution, which then goes to the hydrolyzer. And the hydrolyzer is the point where we actually do make the hydrogen peroxide. But it's not just hydrogen peroxide. So you still have some persulfate, you still have some sulfate electrolyzer in the process. So then we go to the stripper, which then purifies the hydrogen peroxide and allows you to recycle all the residuals back to the electrolyzer. And then since after the stripper, we only have a 10% hydrogen peroxide stream, we have a final step for the concentration of the hydrogen peroxide to the desired concentration to the downstream industry. So we can make 20%, we can make 35%, we can make 50% as required by the industries. So here it is. This is what the TRL6 looks like. The TRL 4 or 5 mini plant looks like. So over here, you see the electrolyzer. And over here on the right-hand side, you see the electrolyzer, the utilizer. Both of these are relatively small footprint units. They can be just forklift on a pallet, moved around. This mini plant has been deployed at Inotex in the Czech Republic, one of our partners. And we have shown that the hydrogen peroxide that we make in this achieves the desired results for the bleaching industry. This unit has now been shipped back to our main developing team for upscaling to our TRL6. So what we're going to be doing is a full automation of this unit. We're going to couple the electrolyzer and utilizer so that we ensure that we have a full feed of the electrolyte through all of the processes. And we're also looking to do further improvements in the energy efficiencies in order to get the most economical process possible. Here are the bleaching results that we got with the hydrogen peroxide from the mini plant. So there was tested on 2 different bleaching machines. One is known as a jigger and one is known as a jet. You see the parameters for the bleaching here and the bath volumes that we used. And you notice here the important KPIs for this process is known as the whiteness degree. So there's a standard called the Berger standard, which gives you a value of how white your material is. And you can see that for both the whiteness and then a full whiteness where they've added optical brighteners to the process, that our hydrogen peroxide is just as good as commercial hydrogen peroxide. We've also been doing LCA studies, looking at the carbon footprint. And this slide shows you how much we've achieved with respect to the state of the art. So our calculations show that the climate change impact of the AO process is around 0.6 kilograms CO2 equivalents per kilogram 35 weight percent hydrogen peroxide. And our hyper process can reduce this by 93% down to 0.04. And it doesn't matter if that the electrolyte in that process is ammonium sulfate or sodium sulfate. Both of them work just as well. Importantly, we've also done studies to determine what the footprint of an AO process would be if you electrified everything. And even in that case, our hyper process comes out better. So and you have an 81% reduction if you have as compared to a fully electrified AO process using renewable energy. I have to point out that the 0.04 here is based on a fully renewable electricity source. So in this case, what we're looking at is approximately a third nuclear, a third wind, and a third hydro electricity. So I hope to have given you an indication of what we're doing in this project. We've achieved this key milestone. It's a deployment of this 4.5 mini plant. It is now back to our mini plant developers, and the mini plant is being upgraded to this TR06 demo. The commissioning of that TR06 demo will take place around June, and then it will go through the TR06 tests that I indicated. The LCA calculations show that the hyper process gives a 93% decrease in greenhouse gas emissions versus the fully fossil fuel AO process, and is even better than a fully electrified AO process. Unfortunately, at the moment, I cannot say that hyper is economically competitive with the AO process, but we expect to see further decreases in that number through these energy efficiency improvements I have indicated, and we hope to get into something that is competitive with the current state of the art by the end of the project. So I'd like to acknowledge the EU Horizon Europe program. You see what the budget is. There are 12 partners involved in this project. 5 of the partners are SMEs from 9 different countries. And we have just started the final year of the project, and we'll be finishing by the end of the year. So I'd also like to thank the Hyper Consortium, and I'd like to thank the opportunity to present the project.
Thank you very much, Richard, for the very interesting presentation on the Hyper project and on the processes and technologies today available for producing hydrogen peroxide. So let's see if we have any possible questions. And also, as a reminder to the participants, please use the chat for general comments and the Q&A box for any questions you may have. I see a question in the chat. So how long it took you to enable the TRL5 from TRL1? What is the purity of water used in the process?
Well, we didn't start at TRL1 for one thing. I would say we started more, let's say, TRL3 to 4. Condias has the electrodes stock, so to speak. So we had a starting point there. We had a starting point with the electrochemical cell. The utilizer development took some time. The project started at the beginning of 2023, and it took us, say, 2.5 years or so to get to the mini plant and its deployment. The water, don't remember exactly, but it's 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 not tap water. I'll put it that way. But there is some purity involved. I'd have to double check to see what we have and maybe answer that question in the chat. Remember that the electrolyte is not just water, but it's also the sulfate and the supersulfate, and so it's you have to have all of these things in solution in order for the electrolysis.
Thank you, Richard, for the answer. So I see some more questions are coming up. Some of them can also be answered directly in the Q&A box. So I see a question about the electricity price. So what electricity price do we use for the calculation?
Yeah, again, that's not a number I have at the top of my head. I would have to, for example, go in and determine what numbers we used for that calculation. I'm sorry, I don't have that information in memory.
Okay, thank you very much. So one last question from Daniel Clue. What is the electricity demand in megawatt hour per ton of hydrogen peroxide?
Oh, you guys are asking very specific questions. I wasn't prepared for this. Again, I would have to go back and look. Our target, if I remember correctly, and was 13 megawatts per. I want to say I'm not sure if it's kilo 100% hydrogen peroxide. We're in that ballpark. And I see, I'll just take this question here, the purity of the hydrogen peroxide after the utilizer. We can go up to 50% purity. But then one of the nice things about that technology is we can, run the distillation column, to the extent that the and downstream industries want to. So if you need, say, 20% hydrogen peroxide to do some sort of bleaching, we can make 20%. If you want 50% to do, some hardcore chemistry, we can do that. It's up to the downstream industries to determine what that concentration is. And that's one of the benefits of having this modular process is you don't, for example, you're not getting it at at your site at 50%, and then you have to dilute it. You get it the way you want it.
Thank you, Richard. Yes, these are very detailed questions. So I would say the rest of them can be answered also directly in the chat box, with the Q&A box.
Yes.
And I remind also the participants to use the Q&A box you find at the bottom of your screen.
And I'll thank Hunk for who's part of the HYFA project for correcting me in terms of the energy requirements.
Yes, perfect. So thank you again, Richard, for your presentation and answers. And we'll now hand over to Teresa Ruka from the ELOXYCHEM Project. Teresa is a research scientist at SINTEF since 2021, where she has been working in the field of innovative conversion technologies. She currently leads the ELOXYCHEM Project and supports its technical development with a strong background in process engineering, drive the project's clear vision for sustainable industrial solutions. So the floor is yours, and please enable the mic. Thank you.
Thank you very much, Marco. Can you just quickly confirm that you can see my screen?
Yes, the screen is visible.
Thank you. Okay, so my name is Teresa, as I got introduced, and I'm here today to introduce you to our ELOXYCHEM project, which is another EU project focusing on electrochemistry. So as most of the EU projects, ELOXYCHEM is an acronym And if you I just want to read out the whole name. It's called Electrochemical Oxidation of cyclic and biogenic substrates for high efficiency production of organic chemicals. And ELOXYCHEM is really all about scale up. So we're taking different processes from a lower TOL scale, and we're developing a pilot scale electrochemical oxidation process to replace some of the chemical conversion processes that we currently have that are relying on fossil fuels or imported chemicals. So we are planning on developing a TRL6 drop-in technology that integrates both the reactor or reactors and the downstream separation, trying to produce market-ready chemicals. We'll also be integrating AI, or put it in different words, a digital twin to optimize the pilot's performance, and we'll work with the integration of renewable energies at our pilot system. So the partners of the ELOXYCHEM project are 10 of number. We have 4 research institutes, 4 small and medium sized enterprises and 2 large enterprises. And we are originated from 6 different countries across whole Europe. And SINTEF is the coordinator of this project. So what are we actually doing in this project? As I said, we are building a first of its kind pilot plant to be used in an industrial environment. And we'll look into using different feedstocks, such as industrial side stream and biogenic substrates, to convert them electrochemically with our ELOXYCHEM technology. Look at their downstream processing to actually receive our targeted products that are carboxylic acid, both monocarboxylic acid, but also dicarboxylic acids. And these will find their application in coating additives, fine chemicals, surfactants, fragrances, dyes, and also polymers for engineering materials. So in the end, from top to bottom in a project, we have this factor 50 pilot scale demo of what we originally started with in the lab. Let's have a closer look at the electrochemical approaches. So we have different process lines in the project, and the first one we focus most on is line 1, focusing on cyclic alkanes and alkenes and their electrochemical conversion into cyclic ketones and dicarboxylic acids. So this is the heart piece of the project, and the final TRL that we aim to reach is 6. We now recently also started to look into our second process line, which is focusing on TOFA mixtures. So TOFA is a shortage for tall oil fatty acids that are a byproduct from the craft process in paper making. And they consist of different C18 unsaturated fatty acids, such as oleic acid or linoleic acid. And here again, our target molecules are different types of carboxylic acid. So this process line will take not all the way to TRL 6, but will target 4 to 5 for this one. And then we have a third process line, which is focusing on a slightly different type of feedstock, biogenic substances or other side streams of relevance that could potentially be terpenes, for example. And here we're looking into dicarboxylic acids with alkyd substitutes. So this is from the development level, the lowest one, and it's also the third, let's say, minor process line to our project. So I said it's about scale up. So first and foremost, it's about scale up of the heart piece of this pilot, right, which is the electrochemical reactor itself. So here we've been through quite a journey already, and we're still in the development stage for the final pilot scale reactor. So we started off, or our project partner, Max Planck Institute, they started up with a lab scale breadth process where they screened a lot of different process parameters initially, and they took it further to the lab scale flow reactor, increasing the electrode area already here by roughly factor 10. And again, screening, optimizing the key parameters that we need for flow conditions. And we now last year took the technology further to this intermediate scale, so reactor, increasing the production rate once more, increasing the electrode area, and are currently in the design phase for the pilot scale reactor, which is why I did not enclose any picture there yet. However, we're targeting a final production rate of 2.5 kilograms per hour for that one, and the electrode area will be in the size of 675 to a bit more than 2,000 square centimeters. That's at least our target. So I thought I didn't want to bore you, everyone, with the structure of our VPs, work packages in the project. So I rather called it interdependencies, because I said it's all about the pilot design, the build, and the testing, but there's a lot that has to fall into place to actually get there. So we do have different work packages to focus on the specification of the single unit operations, the requirements, of course, for the end product validation. We have work packages looking at the different system designs on lab scale for the individual process lines. And of course, as also the block flow diagram depicts, we have a lot of focus and use a lot of time on the process design and the flow sheeting to actually be able to close the mass and energy balances. So when taking something from a rather small scale to a bigger pilot scale, what is most important is to run a health study, to run a safety study on your system, and to ensure that you can do everything possible to avoid any occasions at a later change once you came up in scale. To get to our target, which is the industrial process demonstration, we also have to assess our technology, right? So we have the sustainability and social impact assessment and techno-economic assessment interacting with the design plans that we have, the actual outcomes of our testing, to get to this industrial process demonstration in the end. So we in SINTEF are very strongly involved. We're building the pilot, and we're very strongly involved in the scale up of the technology. So we established a workflow on how we do this. Of course, everything starts with understanding the process, right? You set up a design of experiments to start the data collection, and once you have a bulletproof data set, most probably a bit before you start with the modeling activities that will feed into the design of how the process will look like, how we can build it. And then once we reach the technology development stage of design freeze, we'll start piloting and implementing the units physically to then prove that we have understood the process. Some of you may know there are quite some kinks and challenges that can come up along the way when taking it from a 50 milliliter beaker in a fume hood to 2.5 kilograms per hour scale plant. So what we are very focused on in our work at SINTEF is to combine the technology development with the technology assessment. So at a certain level, we'll use the information that we have from the modeling to feed them already very early into the TEA and an LCA assessment, to be able to refine these models to see if there's any more recycling loops or any more energy integration that we can perform in the model. So we don't necessarily see the TA as knockout criteria for processes, but more like a chance to identify bottlenecks early. So when we now deep dive a bit into the technology development, I just quickly want to guide you through the steps that we are following there. In the beginning, as I said, our project partner, Max Planck Institute, is analyzing and investigating the target reactions intensively. We've been running feedstock studies, screening different operating conditions and specifying what we need the product to look like, what is acceptable for our end user studies. We spent already a lot of time and are still doing on designing the electrolyzer and the reactor. So scanned through different cell configurations and also their flow distribution in these cells. And always in order to make it a scalable process, that it's actually possible to scale it, that to produce a bigger electrochemical cell as we needed for the pilot. A lot of focus also goes to mass and energy integration. We are working a lot on optimizing the feed component supply and the product collection as we're looking into a continuous process. And it's not really straightforward, I can tell you. And from the energy integration point of view, of course, we have to ensure that the integration of renewable energies is compatible and that we have a proper heat management in place. So the next point is downstream separation and purification. Of course, the most focus goes to the product isolation, but I want to also put some focus on the electrolyte recovery and recycling loops, as these are the key points that we can play with to increase the techno-economic availability, and the LCA, of course. The less chemicals spent, the better in general. So for process control and automation, I already said that earlier. We're working with the digital twin of our pilot to help us monitor all the process parameters and define a safety interlock for a safe operation at scale. Which already brings us to the next point: safe operation at scale. We have these HACCP studies, these safety studies in all levels of our scale up to really ensure that we're not overseeing anything. So then in the end, we have the pilot scale data generation where we can track our throughput targets that we've set us initially in the beginning of the project, and we will evaluate the process performance. So how do we do that? We're not only looking at signals that we get from the AI and the optimization there. We also run end-user studies, and these are done from our industrial partners, Evonik and Megara Resins. So they are looking into slightly different types of molecules that we're producing in our pilot. So Evonik pays a lot of attention to specialty chemicals, and they are trying to integrate our ELOXYCHEM molecules as an intermediate for the polymer production, especially for the high-performance polyamides. So they're investigating their properties and check their compatibility with existing product lines. They are also checking the purity of the product with our ELOXYCHEM molecules and investigate the impurity profiles there. So Megara Resins, on the other hand, are doing slightly different. They are looking into the synthesis of polyester resins and alkyd resins for their coating applications. And there they also do a full workup, a full characterization of the derived molecules and test them for their mechanical and chemical performances, accompanied by stability and storage tests. So just to quickly summarize again, facts about the ELOXYCHEM project. ELOXYCHEM is targeting to demonstrate a TRL6 electrochemical process at scale that's in operation for several thousand hours during the project, and that has a stable long-term performance. And thereby, we're not only validating the electrolysis itself, but also the downstream units and the overall key process parameters. We put a lot of focus on the process line 1, as I told you, to be able to deliver an in-spec quality with a design capacity of up to 3.4 tons per annum. We have this digital twin for the pilot, as I told you, and the integration of the renewable energy systems. So all this is feeding into our overall mission, which is to assess the overall industrial feasibility of this process, of this technology, because our vision is to enable this perspective to future scale up to commercial scale. And by that, I would like to thank the whole consortium of ELOXYCHEM and the European Union, of course, for financing the project. And I'm open for questions.
Thank you very much, Teresa, for your insightful presentation. Very, very interesting on the ELOXYCHEM project. So I see some questions in the Q&A box. First of all, asked, what is the raw material source for line 1? So like the raw material, are those bio-based or fossil cyclic alkenes?
For process line 1, so I'll just quickly jump back to the slide. So for process line 1, we actually still have a fossil-based feedstock. However, it's a side stream of the industry at the moment, and currently we're only looking at the process, so the conversion process, to make this more efficient. However, on a longer term, that feedstock can also be resourced from a biogenic substrate, and we have the 2 other process lines looking into the bio-based feedstocks in the framework of this project. Let's put it that way.
Thank you very much. Then I see a question regarding the artificial intelligence model. I don't know if you can address this.
Yeah, I see the question. What is the model used for the AI integration, I guess? Well, this is a very detailed question. I have to be honest. But I can reach out to our AI partner, Prime in the project, and can get back to you with this information.
Thank you very much. One last question. So, which process side difficulties you face in purification downstream? Do you see a minimal viable scale yet? So, about the difficulties on the process for purification and downstream.
Well, which process side difficulties we face in the purification? Well, there are a few. I think the most tricky part in the purification is, again, the scale up, that you might end up having a very nicely working workup procedure at the lower scale, which just doesn't reach the same purity at scale. The large scale purification tests have not been run yet, so I think that would be too early for me to answer this question in that way, I think.
Perfect. Thank you very much again for presentation and answers. I will now hand over to Patrick Fortin from the ELECTRA Project. So Patrick is a senior research scientist in the Department of Sustainable Energy Technologies at SINTEF. He has over 12 years of R&D experience in electrochemical energy conversion devices, mostly within the field of fuel cells and electrolyzers, with recent investigations into the electrochemical production of ammonia. His work aims to bridge fundamental materials chemistry with device-level performance to develop next generation of decentralized electrochemical ammonia production systems. So whenever you want, Patrick, the floor is yours. Enable the mic. Yes.
Thanks, Marco. Good morning, everybody. Yeah, so today we'll talk a little bit about the electrochemical production of ammonia and look into more specifically the project that we have granted through the EIC Pathfinder Challenge Program called ELECTRA, looking at a new electrochemical concept for mid to long-term storage of electrical energy in ammonia. So I really like this figure because it gives us a nice overall sort of answer to why we're interested in electrochemical synthesis of chemicals, which is the topic of this webinar in general, and then more specifically, why ammonia is so interesting to us. So if we look at the chemical industry as a whole, it's responsible for roughly 10% of the world's energy demand and 7% of the greenhouse gas emissions. So as a single point source for an industry, that's quite significant. And these are the top 5 sort of most energy consuming and emission producing chemicals. We have ammonia, ethylene, aromatics, propylene, and methanol. And specifically 4 of these 5 in ammonia, ethylene, propylene, and methanol all have something in common, and that's that they can be produced electrochemically. So looking at ammonia, we can see the electrochemical reduction of nitrogen to ammonia has been shown a few years ago in the journal Science. CO2 conversion to methanol, electrochemical reduction of CO2 to methanol in NatComs a few years ago. This has been around for a while now, but a lot of these are fairly recent in terms of investigations into these processes, and are in high impact journals, right? So again, we got CO2 conversion to ethylene in Nature Energy a few years ago, and then the electrochemical synthesis of propylene from CO2 in NatChem a few years ago. So high impact because electrochemistry allows us to reduce both the energy consumption and the greenhouse gas emission. In some cases, these processes, not only are they carbon neutral, they're net negative. They're consuming CO2 to make a value-added product. And if we look at ammonia here, so ammonia is labeled as number 1 in terms of production volume. It is one of the most produced chemicals in the world, and it is one of the most energy consuming and greenhouse gas intensive processes in the entire world. So if we are able to develop electrochemical methods towards ammonia synthesis that can reduce energy consumption and reduce greenhouse gas emissions, that will have a huge impact on society. So where do we use ammonia? Right now, most of it is used in agriculture. We produce about 175 million tons of ammonia per year, where 70% of that ammonia is used as a fertilizer. But more recently, there's been a lot of interest in ammonia as a fuel, especially for maritime transport. It's interesting because ammonia is a globally traded commodity. We know how to transport it, we know how to store it safely, and it's much cheaper to transport and store than hydrogen right now. So you can use it in direct combustion engines. So you can do some modifications to a 2-stroke diesel engine and enable the direct combustion of ammonia to produce nitrogen and hydrogen. So again, CO2-free combustion. And this is considered a transitional tech in the near future because right now it's cheaper, power densities are good, load response, robustness. But towards the future, there's an eye on using fuel cells. So both direct ammonia fuel cells, for example, these high temperature solid oxide fuel cells can use ammonia as a fuel, decompose it electrochemically to make electricity that can then be used to run an electric motor, for example. Or you can have an ammonia cracker on board in conjunction with a proton exchange membrane fuel cell. That ammonia is cracked into its constituent parts of nitrogen gas, hydrogen gas, and you then get your hydrogen as a fuel in PEM fuel cells. So this is something that's sort of into the future on the near horizon that people are starting to be very interested in for ammonia use. So how do we produce ammonia? Right now, Haber-Bosch, this is the main method of ammonia production. So we have our Haber-Bosch reactor here, typically performed at high temperatures and high pressures, 400 degrees Celsius, 200 bar. This leads to both significant capital costs in terms of energy production or energy consumption. as well as the source of hydrogen. So for the Haber-Bosch reaction, we combine hydrogen, we combine nitrogen. This is a thermochemical reaction that then produces ammonia. And the hydrogen that's currently used, as Richard mentioned, comes from fossil-based sources. So typically we have methane, we put that through the steam reforming process, that carbon from the methane and becomes carbon and CO2, and the hydrogen becomes hydrogen gas. If we are able to capture the CO2 emissions, then we can label the ammonia that's produced as blue ammonia. And then if we are able to replace this steam methane reforming with a renewable hydrogen source, like coupling water electrolysis to renewable energy inputs to make green hydrogen, we can call the ammonia green ammonia. And this now is obviously the goal, less carbon emissions, but we typically have it's typically more expensive because hydrogen from electrolysis is going to be more expensive than hydrogen from steam methane reforming. Now, in the ELECTRA project, we're taking this one step further, and we want to replace the Haber-Bosch reactor with an electrochemical reactor that allows us to produce green ammonia at ambient temperatures and low pressures. And so this is the concept here. And so the main objective is to use green hydrogen as a feedstock in order to make green ammonia. And we're going to do this electrochemically. So this little cartoon here shows us the general concept of the electrochemical ammonia production step. Here at the anode, this would be where our green hydrogen feed comes in, and hydrogen is oxidized to produce protons. Those protons move across a proton exchange membrane where they're combined with nitrogen at the cathode and reduced to form ammonia. And so within the ELECTRA project, there's sort of two main parts to this project. The first is going to be developing what you see in this cartoon here. This is what we call the membrane electrode assembly. So we have a proton exchange membrane, and on each side it's going to be sandwiched between a catalyst. So we're looking at new catalysts to develop, specifically critical raw material free hydrogen oxidation reaction catalysts to perform this initial conversion of hydrogen to protons, and then also looking at CRM-free nitrogen reduction reaction catalysts here. Membrane development as well. Things need to be tuned very specifically. So there's a lot of know-how from both the electrolyzer and the fuel cell side of things to run this, but we need to tune things a little bit more specifically to enable this reaction here, as well as looking at different engineering designs of the electrochemical reactor itself. Things are a little bit different. Things need to be a little bit more corrosion resistant to ammonia. There is a little bit of pressure involved. And so the key challenges are really the kinetics. So looking at the cathode reaction here, this electrochemical nitrogen reduction reaction, this is a 6-step. This involves 6 proton coupled electron transfer steps. So this means that kinetically, this is very, very challenging. Nitrogen has to come in, it has to bind to the catalyst surface. Then you have to activate this nitrogen-nitrogen triple bond. This is a very high energy bond, so this is difficult to do. And then you have 6 different electron transfers. So you're transferring an electron and a proton coming in at the same time. And then you have to do this all the way through until you get ammonia and it's desorbed from the system. So it's very difficult kinetically. Also the selectivity, right? So I mentioned we do have protons as a source for this reduction reaction. And so in the catalyst layer, you're going to have a ton of protons around and selectivity. So what's going to happen is the protons can actually just be re-reduced back into hydrogen gas. So you get this reverse reaction happening here. And so your selectivity goes down if you're only producing hydrogen and no ammonia. It's not very useful if the goal is to make ammonia. So we suffer from low Faradaic efficiencies, and that's generally an issue. So you have to tune the catalyst, the electronics of the catalyst, and there's a lot of work that goes into the catalyst development here to have the right balance of activity and selectivity towards the nitrogen reduction reaction. So this is what we're working with. Yeah, a lot of fundamental materials development and electrochemistry. So a lot lower on the TRL scale than some of the other things that we've seen, but together with Aarhus University, who are coordinating the project, SINTEF are the research organization in Norway where I'm working. VITO is the research organization in Belgium. C2CAT is a Dutch startup looking at catalyst development. Edicio is an end user of ammonia, so they actually use ammonia to synthesize amino acids and use that in animal feeds. And Nori is a renewable energy company out in Greenland. They're doing all the project portfolio management for us. And Electronic Fuel Tech is a Danish company that does a lot of development with e-fuels. So that is sort of the project in a nutshell. So just to quickly summarize, ammonia production is an energy-intensive process and produces a significant amount of carbon emissions. The electrochemical synthesis of ammonia has the potential to reduce the energy consumption and the emission compared to Haber-Bosch process, and the ELECTRA project is developing innovative cell components and reactor designs to enable the electrochemical synthesis of ammonia. So with that, I'd like to thank the funding agencies and the project partners, and thank you all for your attention. I'd be happy to answer any questions that you have.
Thank you very much, Patrick, for your presentation. Very, very interesting on the ammonia production and on the ELECTRA project. I don't see any specific questions from the Q&A box. So I would say we have anyway time at the end for a discussion. So I would go to our final presentation now. And anyway, any questions can be also answered directly in the Q&A box. Okay, just one I see in the Q&A box, and then I hand over to our final presenter. So one question, for instance, it's asked, why don't you try with the lithium-mediated way?
Yeah, this is something we're definitely also doing in conjunction. Lithium-mediated, the issue with that is that your reduction potential of lithium is 3 volts. So your total cell voltage after kinetic overpotentials, you end up with something like 4 volts of cell voltage. So your electrical efficiency is very, very low. Hydrogen and nitrogen is theoretically a spontaneous reaction. It's an electrolytic reaction. It's a galvanic reaction. So the overpotentials are going to be much less. Selectivity is an issue. It's much more difficult. The general consensus is that this is nearly impossible to do without the lithium-mediated way, but the lithium-mediated is also something that we're looking at in different projects.
Thank you again, Patrick, for presentation and answer. So I will give the floor now to our next presenter, Francisco Mendez Alva, for the FIREFLY project. Francisco is an innovation and grant consultant at P&O Innovation in Belgium. He supports the development of innovation proposals and consortia across multiple EU funding programs and advises EU projects on exploitation and clustering strategies, including FIREFLY. So whenever you want, Francisco, the floor is yours, and please enable the mic. Thank you.
Thank you, Marco. I will start sharing my screen. The title of my presentation is Sustainable Transitions for the Catalyst-Based Chemical Industry. That's basically the vision from the FIREFLY project. So let's take one step back and talk about the motivation catalyst in the chemical industry. So basically, at the heart of the chemical industry lies the reactions at the reactor, defining a downstream separation needs, heat transfer needs, and fluid mechanic needs. And at the heart of the reactor are engineered materials that make these reactions feasible, so lowering activation barriers, stabilizing intermediates, and steering selectivity. Without these catalytic materials, process would demand excessive energy, extreme operation conditions, generate large amounts of waste, or trigger undesirable side reactions, compromise efficiency, environmental impact, and operational safety. So in this sense, the sustainability of the chemical industry is inseparable from the sustainability of its catalyst. And basically, catalysts are used in 90% of the chemical processes. In general, in 60% of industrial products. And Europe remains as one of the largest producers globally, actually the second one by sales. The catalyst industry in Europe has growth projections. However, those are hindered by socio-political issues like the use of critical raw materials and the strategic foreign dependencies, well, specifically or more intensively with energy. So when we are talking about catalysts, we typically need to refer to materials such as the ones in the platinum group metals and others that normally are classified as critical by the European Commission. So the vision of FIREFLY is improve the sustainability of key chemical processes via electrification and circular electrocatalyst. So in the project, basically 4 product groups are selected in order to recover the metals that are involved in the catalyst that they use. They are not the state-of-the-art routes. They are also new routes that are proposed in the consortium. So they are alternatives to the current mostly fossil-based options. So part of the vision is the electrification and decarbonization of this process and to enable more sustainability and circularity in the chemical industry. So the project basically starts with an industrial driver. So basically waste, spent, and off-spec catalysts from the industrial partners. And then we go for what we call the toolbox. That is the collection of technologies that are in the project in order to treat and recover the valuable materials in the catalyst side streams. Then we have this validation stage in which we build a small scale pilot, modular, compact, industrially relevant. So basically, previous to this pilot, there was a benchmark of the toolbox. What are the most suitable technologies that can get into the modular pilot? And then finally, we have the end users, sustainability, sustainable electrochemical processes. They are ammonia, hydrogen peroxide, biomass processing, and lignin polymerization. All of this is in the context of electrification with renewable energy sources. So basically, there is a platform in which these different technologies connect in order to see how they can be operated with renewables, either with a direct connection, exploring PV and wind energy profiles, or making use of redox flow batteries. So basically, this is the consortium that we have. The project has been running since January 2023, and it ends with the end of this year. It's coordinated by Vito here in Belgium, and it's going from organization from Iceland to Greece, 8 research organizations, 6 SMEs, and 2 large enterprises. So this is the core of the presentation. So let's go part by part. In the first part is the waste specs catalyst. So basically we have 2 main groups, the heterogeneous ones that are solids and the homogeneous ones that are liquid. The heterogeneous ones are basically Denox catalysts from power plant from Engie, and also off-spec catalysts from Johnson Matthey in the production. Johnson Matthey is one of the largest producers of catalysts in Europe, and ammonia is an SME working with the production of ammonia from the atmosphere. So they have this innovative process to do it, and they are looking for the circularity of their catalyst. So the toolbox, what we call the toolbox, is constituted of multiple subgroups: electrified pretreatment, electrified metal dissolution, electrified metal separation, electrified metal recovery, electrified metal recovery continuation. So only like for this additional one. And so for the different subgroups, we have multiple technologies from different institutions. MCP stands for mechanochemical processing in Q Leuven, electrochemical from Technalia, electrosolvol leaching from Q Leuven, for the electrified metal separation, and then for the electrified metal recovery, we have a collection of technologies that are the core, and they were basically competing in the process in the project to see which ones were the best for the multiple applications. Basically, one of the key conclusions is a combination between MCP and GDEX came to be one of the most, actually the one that is selected for scaling up. The electrocatalyst formulation is the next step. And finally, we have the application in the multiple, so the fabrication of the catalyst, and then to test with each of the products, actually the performance of the let's say catalyst from secondary resources. Yeah, part of the project includes the integration of a integration of renewable energy sources, a prediction tool. So basically, for the toolbox, so everything is embedded in a platform that enables that we don't need to do always experimentation and explore, for example, alternative streams without to then go to a next level of exploration with experiments. The modeling and engineering. So basically, the development of the models that then is translated to this toolbox, and the integration of life cycle and sustainability. Yeah, just like in this terms of user interface, we have two main ones: one based on the toolbox, the material side, let's say, and another one based on energy. So to see the integration of renewables. So overall, the expected impacts are related to the improved recovery. We have the specific impacts for specific KPIs for the different technologies, and also the integration of renewable electricity. We want to provide the assessment of this energy savings. Yeah, well, one of the key drivers for this energy savings is the avoidance of hydrometallurgical processes or the extraction methods comparing with primary options. CO2 emission reduction, also under assumptions of a fully renewable energy power grid, and competitive cost. So we have the capex and opex analysis for each of the routes for the products. Some of the results that we have. Currently, we are in month 36, so the routes are selected, and we are working on the demo. We have been doing, for example, the mapping of resources in terms of Denox catalysts across Europe. So beyond the scope of the companies in the consortium, testing in demo cases. So, for example, lignin, the polymerization options, even got improved results compared with the original catalyst, and recycled catalyst from biomass conversion. In terms of electrified technologies, basically the assessment. So they have the recovery rates for the key elements in the multiple catalysts. And we did a benchmarking, so not only comparing with the technologies within the consortium, but also the process outside of them. And yeah, basically one of the key conclusions is that they perform better in terms of energy, and in terms of they have similar performance for the recovery, but in terms of capex and opex, there is still work to be done there. And finally, the sustainability assessment, in which the tertiary extraction leads to lower environmental impact, and then the neutralization of chemicals results in lower impact. So added modules to the process design. In terms of energy requirements, the analysis of the vanadium redox flow battery, the techno-economic analysis, the prediction toolbox, the modeling and the exploitation, stakeholder analysis, key exploitable resource, and the clustering to steer the project towards industrial demonstration and exploitation. That's part of what I'm doing today. In general, barriers for implementation, like thinking about the end of the project, overall, the framework is convenient for the kind of technologies that are involved there. However, it's necessary to keep the consistency with environmental regulations, and pressure towards electrification is just essential. The competition with established routes. So the CapEx cycles in companies is something to take into account to enable more interest from the industry, and of course be aware of the technology lock-in. Actions require engagement of stakeholders with high industrial involvement in road mapping exercise, for example. We have actually one next Friday. It is only for the FIREFLY project, with experts invited for the roadmap. In the website, in about 1 month, there will be a newsletter about the outcome of this roadmap. Another action requires integration of individual technologies in strategic industrial processes. So it's like a more industrial driven approach. How given the current infrastructure, how this specific technology could be implemented in the site. Testing of small pilots, scale up beyond TRL6. That's the aim of the project. FIREFLY is expected to land TRL6 pilot, and industry supporting infrastructure. So there's benchmark with the different technologies. That's it. Thank you.
Thank you very much, Francisco, for your presentation. Now we have roughly 10 minutes to answer questions, both on FIREFLY project or the other projects. Let's see if there are any specific questions on FIREFLY. For now, I don't see any specific on the FIREFLY. So maybe I can employ one question from the Q&A box, which was already answered. So to any of you who wants to answer, that is regarding renewable energies, because Francisco also mentioned earlier the renewable energy topic. And this question says, since the projects rely on electrification to replace traditional thermochemical processes, how do your technologies or projects handle the volatility and intermittency of renewable energy sources like wind and solar without compromising the stability and purity of the final chemical products? If any of you wants to answer these live. I see the hand raised by Francisco.
Yeah, well, basically the approach that we have in in FIREFLY is to either deal with the profiles and see how they impact the running of the process, or the alternative with the vanadium flow redox battery. So it's like, yeah, one of the tools. Currently, we have not conclusive, but including results on this. If, or for example, all the technologies in the project can go directly with the, but most likely not.
Okay, Francisco, thank you for the answer. If there are any other answers from the presenters. Okay, otherwise we can, Richard, please.
Sorry, there. I wrote my answer in the Q&A, but I can just repeat what I said. For Hyper, it depends a lot on what the downstream process is and how much product they necessarily need. But also, we're making hydrogen at the cathode, and we're looking into how that hydrogen can be exploited to soften those peaks and valleys in terms of the, or at least the peaks and the valleys in the renewable energy availability, so that you use the hydrogen instead in some form or fashion. We have some nice numbers on that, but I can't really say any.
Thank you, Richard. Okay. If you have any other answers to these, or other questions that you can find in the Q&A box. Yes, Francisco.
I have actually a question for the other projects representative here, if they would like to actually go for a joint publication regarding this specific issue of the integration of the renewables in emerging technologies. Because it's something that we see across all the technologies that we have, and maybe something that is worth like discussing a bit, and then go, like, for example, to a white paper or any sort of joint publication in that sense. But I would like to hear something from you here, if the direction is right, or is like, well, not really interesting for you.
For Hyper, I think that would be of interest. We also have a white paper as part of our project, and I think there may be some overlap, so we should have a chat later.
Okay, great.
Maybe we can. Will you be in Brussels on Friday?
Yes.
Because if so, we can have a chat then.
Yes, Teresa.
Yeah, so if I may, just from the ELOXYCHEM perspective, I mean, that will definitely be of interest from our side too. We were planning on integrating this part of the project as a fraction of the chemistry optimization paper, but it can, I mean, it's always nice to link EU projects together, so that would definitely also be a viable option for us. I know that especially the EU likes to see some interaction between the projects when there's overlap, and here obviously there is, so we should make use of it. That's a very good idea. Thank you for taking it up.
We will follow up in this.
Yes, thank you very much for this. Was a wonderful idea, Francisco. And so our time is almost over, and so I would like to give a huge thank you for your time, and to the participants for the brilliant questions, and all the presenters for presentations. As we close, look out for the follow-up mail we received with the recording and all the resources that were much mentioned early on. And yes, again, thank you. I think it was a very interesting discussion to put together all our projects and joint efforts in this direction for a greener chemical industry. So yes, thank you again very much, and see you soon.
Thank you, Marco. Bye.
Thank you.
Okay.
Thank you.
Bye-bye.